All right, this is from 2016. So we have a table. It's describing water being pumped into a tank. And it gives you an equation for the water being pumped into the tank. And then it gives you a table of a different equation of water being removed. And it says they're starting at 50,000 liters before the water is being pumped out and water is being removed. All right. Part A, estimate the derivative at 2. So using a table, how do I estimate a derivative? I find the slope. Where's 2? What are the two numbers around 2? And then find the slope. y2 minus y1. x2 minus x1. That's it, and remember your units. So for 1A, it's going to be 950, subtract 190, and 3 take away 1, don't have to simplify it, and the unit would be liters per hour. Per hour. So because you're taking the derivative of a derivative, liters per hour, the derivative would be liters per hour, like acceleration. All right, let me show you what mine looks like, then we'll look at number 2. Just like that. All right, part B. And if we need to simplify that, we will later on if it's required. Remember, question number 1 is a calculator question. So 1 and 2 are calculators, 3, 4, 5, 6 are not. So number 1 in 16 again, this was a calculator question. All right, use a left Riemann sum with intervals there to see how much is the total amount of water removed from the tank during the 8 hours. So we're going to do a left Riemann sums. First of all, we write down what we're doing. So we're integrating from 0 to 8, and we're going to integrate r at t dt. Then, after we write down what we're doing, what is a left Riemann sum? How does that work? So these are rectangles. The t, or the x coordinate here, is my width. So from 0 to 1, the width is 1. And then the left height, so I use 1,340, plus the next width from 1 to 3 is 2, and the left height is 1,190. And then I'm going to follow that pattern, and I'll show you my work. 3 to 6 is 3, and the left height is 950. One more time. 6 to 8 is 2, and then the left height is 740. Don't even simplify it, and at the end I'll include the units if needed. And then it says, is this an overestimate or an underestimate of the total? So for a Riemann sum, to understand if it's an over or underestimate, I need to know if it's increasing or decreasing. So if I look at the rate, you can see it is decreasing all the way through. So let me show you my work. If it's decreasing, what does that mean? So first of all, here's my work. I show what I'm doing. I then do a left Riemann sum. And so I'm going to write this down. Since is decreasing, and then I'm going to give myself a picture to understand, is that an over or underestimate for a left Riemann sum? So I'm going to draw something decreasing. If I do a left Riemann sum, so that means the left corner is where I draw my rectangle from. I want you to notice that when it's decreasing with a left Riemann sum, it's over the line. It's an overestimate. If it was increasing and you did a left Riemann sum, I want you to notice it would be an underestimate because it's under the line. So I just draw a picture to remind. If it was a right Riemann sum, it would be flipped the other way around. But for me to remember, I draw a picture and draw a left Riemann sum and go, oh, that rectangle's overlined. It is an overestimate, and that's why. So since RT is decreasing, it is an overestimate. All right, part C. Use your answer for part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So first I need to know how much water did I start with, which is 50,000. So I start with the number 50,000. How much is in the tank to begin with? Then I plus the water going in. So water is being pumped in at this rate. So I'm going to integrate from 0 to 8 that rate of water going in. And then I'm going to subtract the water that's being removed. That's R at T from 0 to 8. So this is what it looks like. and then I'm going to use a calculator to finish it off. So we started with 50,000. This is the rate of water going in. So if I integrate it from 0 to 8, that's the amount going in. Subtract what's being removed. This is a table. We actually did this in part B. And then I'm going to put all that in calculator right now. So I'm going to go to Desmos and get an answer. So there's my equation. You can press pause if I'm ahead of you, but I typed the equation in already. That's for water going in. Then I'm going to type in. So this is 50,000 plus, I'm going to integrate. So I'm going to go down here to calculus and integrate. And I'm going to integrate from 0 to 8. And that, I don't have to retype it in. I'm just going to call it that, R at TDT. Then I'm going to subtract. Now I'm going to use parentheses here. I'm going to subtract what's removed. That's that Riemann sum that I did in part B. So I'm just going to copy what I did in part B. So that's 1 times 1340, that's what that is, plus 2 times 1190, plus 3 times 950, plus 2 times 740. And that will tell me the total amount of water that was in the tank. So it is 49,000. And again, I'm going to round. Does it tell me how to round? It says to the nearest liter. So it's telling me whole number. So 49,786 liters. All right, part D. What it looks like. In part D it says, from 0 to 8, is there a time when the rate at which the water pumped into the tank is the same as the rate at which water is removed? To understand this, we're going to look at the ends of the rate. Like for the rate of removal, at 0, the rate is 1340 liters per hour. And at the end, the rate is 700 liters per hour. For going in, I'm going to do the same work for 0 and 8. And I'm going to look at the values. And since it is differentiable, it's continuous, if they switch, like if this rate is bigger to begin with but smaller to end, there has to be a time where they cross where they're the same rate. That's how the intermittent value theorem works. Okay, so let's use our Desmos again. I already have it set up, so it's super easy. I can just type in W at 0 and get an answer, which I already knew was 2,000, and then W at 8, which I didn't know. And again, to 3 decimal places, I'm going to do that. So the rate going in starts with 2,000 liters per hour. Then at the very end, it's 81.524 liters per hour. And then we're going to write a statement. So there has to be at least a time. So there must be at least one time from 0 to 8 when R at T equals WT, because R at 0 is less than W at 0, and W at 8 is less than that at 8. This is called the intermediate, and you can use letters, the intermediate value theorem. So at first the R rate is smaller, and then at the end the rate of water going in is smaller. So there must be a time where they cross in that. If one is bigger and then the other is bigger, there must be a time in the middle, at least once, where they're the same rate. All right, one more. 2015. We'll do 2 on this video. All right, let's look here. I was ready for 2015. Let's zoom in here. So again, these are questions used in each year. So this was the one used in 2015. So here you have a table. Joanna jogs along a straight path. Her velocity is given. It's differentiable, which means it's continuous. and it's measured in meters per second. Step 1, easy question. Can you find the derivative at 16? So press pause and do 3a, then press play. So 16 is in between 12 and 20. To find the derivative off a table, you take y2, it's slope, y2 minus y1, x2 minus x1. So we're going to go 240, take away 200. Don't simplify it. 20, take away 12, and then the unit, which is meters per minute per minute. Let's write this properly and I'll show you. So always start with what's being asked. So the derivative of v, approximately, you're doing the slope formula, and it's meters per minute like acceleration. It is acceleration, it's velocity. All right, part B. In part B, it says, using correct units, go back here. What's the meaning of this? So if you integrate velocity, absolute value, that's going to give you the total distance. The other word is displacement. So absolute value gives you the total distance. Whether you're going forwards or backwards, right or left, what's the distance you went in any direction, and it adds it up. So all the velocities are positive. So what's the meaning of it? So we need the word total distance. So for the, I'm going to write down what it is. 0 to 40, absolute value of v at t is the total distance Joanna jogged over 40 minutes. Beautiful sentence. Then, can you find it using a Wright-Riemann sum? So I'm going to write it down again. I'll show my work in a moment. And then what is a Wright-Riemann sum? So 0 to 12. And notice the questions that get repeated over and over again. Okay, from 0 to 12, right is 200. From 12 to 20, that's 8. And a Wright-Riemann sum is 240. From 20 to 24 is 4. And a Wright-Riemann sum is positive 220 because of the absolute value. So this is the one that's going to, any negative numbers will become positive because of the absolute value. And then 150. So then it's 24 to 40. So it's 16. So the distance from 24 to 40 is 16. And use 150. You don't have to simplify it. There's your answer. Part C. Let me show you my work. And at the end, I'll make sure the units are included. So press pause if you need to, but that shows what the meaning of it is, and then you found it using a Wright-Riemann sum. Part C. Someone's riding a bike. So Bob's riding a bike, and you have an equation. I'm going to write that equation down. T cubed subtract 6t squared plus 300. It asks to find the acceleration. So the acceleration is the derivative of velocity. So I'm going to take the derivative, super easy, 3t squared minus 12t. Then I'm going to plug in 5, not simplify it, and I have my answer. Make sure my units are at the end, I'll make sure. So this is what it looks like. So I took the derivative of the velocity, and then I plugged in 5, and then I'll do units at the end and make sure they're right. All right, last one, part D. Read it first, press pause. Based on the Model B, find the average velocity. That's another way of saying average value, and that's an integration question. So to find the average velocity or average value of the velocity, we integrate from 0 to 10, and we're going to integrate that velocity, which is t cubed minus 6t squared plus 300. And then I divide by the difference of the bounds. So I divide by 10, take away 0, and that will give me my answer. So let's do the work for that. Again, we're not going to simplify much. So this is average value. That's the setup. You integrate and then divide by the difference of the bounds. I'm going to write in, instead of divide by 10, I'm going to write 1 over 10. And then b at t is t cubed, subtract 6t squared plus 300, and then I'm going to go to work. So to integrate, we're going to add 1 to the exponent and divide. We're going to add 1 to the exponent and divide. I'm not going to simplify. 300 is 300t. And then I'm going to integrate from 0 to 10. Again, I'm not going to simplify here. I'm going to plug in 10 first. Subtract, use parentheses, plug in 0. 0 actually gives me 0. If you can't see that, then plug in 0 for each one, and you get your answer. Now I'm going to make sure my units are right. So the average velocity, so this is meters per minute. Done. That's that answer. Back here, part C. This is acceleration. So this is meters per minute, because that's acceleration. I don't have to simplify it, but that's what it is. Here, total distance. This, I'm going to put parentheses around it, is just meters, or m. And I already put units there. We're done. Mr. G Math over and out. I'm proud of you. You're working hard. It's not wrong to do it again, a second time by yourself, and look at the video again until you really understand it. Till next time.